Okay, good evening, everyone. Couple of announcements first. If you guys are students here, we have a bunch of former COD NIU students, so thank you for being here. The rest of them are COD students in different classes, and a couple of old faces, including my own. I do want to say a couple things as by way of announcements. We are trying to upgrade and make sure that our attendance sheet, or not the attendance sheet, but our club membership is up to date. So if you are an AMS member and have not responded to any of the emails we've been trying to send out, please send me an email at servatka@cod.edu. Also, please pay the membership. We're asking $25. It's payable via Venmo or Zelle. Check our Chicago AMS media sites. We have X, Facebook, and Instagram, and there's QR codes, and you can do Zelle or Venmo. Or you can, Patty, the old-fashioned check way also works. For students, we are offering a student membership. We're just trying to get some commitment by having people buy into it. So it's a $5 membership for the year, and you can be a member of the Chicago AMS. Also, the COD AMS. John, can you announce just a little bit on the, or Aiden, on the calendar? Would you do it? Okay.
So one of the projects we do at the COD AMS Meteorology Club is we do this calendar every year, and we are currently collecting photos to feature in the calendar. If you are willing to submit them, we currently have a Google Drive. I believe we will be posting that. We've sent out an email, and if you do not get that email, let me know, and I will make sure you get one.
Also, we are going to be bringing back, for some of you would know this, hopefully the DuPage Northern Illinois Skywarn Advanced Spotter Training coming up this spring. So we are in planning of this event. At least we're hoping to do this. And we do have Roger Edwards, who is scheduled to come and be here. Roger is going to be retiring from the Storm Prediction Center, and he's probably one of the great severe weather meteorologists of all time. So, and he's super interesting, very fun, and really knowledgeable. So that'll be coming up in March, and we'll be working with DuPage EOC and all that other stuff, Homeland Security. I'm going to turn the floor over to Nick, the vice president here, and he's going to talk about something I think is going to be really great, and then he'll introduce our speaker for the night.
Hi, everybody. So I just wanted to tell you guys about a fundraiser we are doing. So just 2 weeks ago, as you all may know, Hurricane Helene impacted the Southeast, and it really hit a lot of communities hard. Tonight, Hurricane Milton is on the verge of making landfall in Florida. So Paul and I thought it would be a great idea to create a fundraiser, and this fundraiser idea was after Helene, and now we have Milton. So we decided it would be better to make this a fundraiser for both. The fundraiser is named Together We Weather, and on the back of the t-shirt, it says, "When life gives you weather, build community." And so for us as Chicago AMS, this shirt encompasses who we are as a group and why we are doing what we are doing here. So with us being a community, it's also important to know what we can do to help those affected by these disasters in any way that we can. So the words on the back of the t-shirt also hold that meaning as well. Therefore, with this fundraiser, all proceeds, so 100% of the proceeds that we get, that we make, will go to the American Red Cross to help with emergency relief efforts and rebuilding homes, providing essential needs to families in need. So the shirts are being sold for $25 plus shipping, so got to add that in there. And through Custom Ink, the shirts will be directly shipped to you, to your own house. And if you don't want to buy a t-shirt, there's always an option just to donate on the Custom Ink website. So that's a great thing. So you can scan this QR code right now, or you can get the link from an email that I'll send out either later tonight or tomorrow morning. The fundraiser will be open 20 days from today, so you can, if you can, please help share this fundraiser so we can get as many people to help out as possible. Together we can help weather these storms, together we weather, and bring hope and healing to those affected by Hurricane Helene and Milton. So with that, we hope that you can join us in helping make a difference with this. So switching gears, if you guys, if you haven't scanned that, I'll just send the information. But switching gears, we do have our guest speaker tonight. His name is Borchardt, and he is from the National Weather Service in Chicago. Well, technically Romeoville, but he is going to be talking about damaging winds from elevated convection. So it should be a great talk, and I'm going to turn the floor over to him.
Actually, I think I'm going to put this down. Can you all hear me okay? Yep. All right, awesome. Well, thanks for coming. First, kind of interesting that we're here to talk about weather on the eve of another potentially historic weather event in the country. Second major hurricane making landfall in the span of just a few weeks. I always feel torn when these kind of events happen because as a meteorologist, it's fascinating to watch a hurricane drop 80 millibars in the span of 24 hours. That is like incredible. But the human toll of it, it's really difficult. And I think there's going to be some difficult images coming out of Florida, maybe not right away if they lose power and whatnot, but over the next few days. And you factor that into what happened to the residents who were hit by Helene, it's pretty tough to see. So just something to keep in mind as we appreciate the weather. But thank you for the introduction. Thanks for welcoming me here to speak to the chapter. My name is Brett. I'm a meteorologist with the National Weather Service in Romeoville. That's an important distinction, I guess. I'm a lifelong resident of the Chicago area, aside from when I went to school. Born and raised in DuPage County, big fan of the community here, and really big fan of the website that's maintained here. I've been using it since I've been in middle school, so pretty happy that I'm able to, I guess, give back to the community here and talk about something that's very near and dear to my heart, which are damaging winds produced by elevated convection. So it's a mouthful. Why don't we get started? Let's see if I can figure this out. Okay, perfect. All right, so let's talk about thunderstorms. I think most of us in this room are pretty familiar with thunderstorms, but it's good to always review. We all know that thunderstorms have a few necessary ingredients to develop. They need lift, moisture, and instability. Now, when we're talking about instability this evening, we're talking about upright instability or thermal instability. That's an instability that is derived from a difference in temperature with height. So we all have seen hot air balloons that are rising. It's because it's warmer inside the balloon compared to outside the balloon, and that's what's going on in the atmosphere. There are different types of instability out there that can generate thunderstorms. One is called slant-wise instability. We're not going to talk about that tonight, but that's how you can get thunder snow and big snowstorms. We're mainly concerned with temperature differences this evening. So once you have instability in the atmosphere, you also need moisture. It's related to instability, but moisture is like pouring gasoline on a fire when it comes to thunderstorms. For every degree you increase in your dew point, you actually get more bang for your buck for every degree you raise in your air temperature. So literally, it just makes thunderstorms bigger, meaner, faster, stronger. And of course, you need some sort of lift to lift your parcel or box of air to generate a thunderstorm. Now, when we're talking about instability, it can be present at multiple levels in the atmosphere. All of us live on the ground, whether you're in the mountains or flat Illinois, Iowa, Midwest, this general area. We have to realize that the temperature changes with height, and we look at the temperature difference all the way up to about 50, 60,000 feet in the atmosphere when we're forecasting. So when we're looking at the temperature difference with height, we're also looking at where there is instability. So where are there pockets of air? If you were to rise, that pocket of air, is it warmer than its surrounding environment? When we're talking about surface-based instability, that is when we're talking about air that's originating from near the ground. We measure that with surface-based CAPE, SB CAPE, or a mixed layer CAPE, ML CAPE. They're both pretty similar. Mixed layer is just a slightly deeper layer near the ground. And surface-based instability is typically what most people look at when forecasting severe thunderstorms. But there's also elevated instability, and that's when you have a pocket of air above the ground that is unstable. We measure that using mu CAPE, or most unstable CAPE. And elevated instability is what I think is a little bit more interesting. It's a little bit more sinister, harder to find from time to time. And that's what we're concerned with tonight. Now, a thunderstorm actually doesn't care where instability comes from. All it cares about is that there's instability and it's cold enough to generate lightning. That's roughly about minus 20 degrees Celsius. That's kind of a weird number, but that's where you have enough mixed phase precipitation, graupel, to get friction and generate lightning. But a little point I want to make here is you can still have convective processes in a thunderstorm when you don't have lightning. So convection really describes the airflow that results from temperature differences. So if you're going to be making like pasta after this or having spaghetti some other time, if you put a pot of water on a burner or turn the burner up, that water is going to undergo convection, right? The bottom of the pot gets hotter, the water wants to rise, you get these vigorous thermals, that's convection. Thankfully, you don't have lightning bolts coming out of your pot of water. That would be really awkward and uncomfortable. But it's the same process in the atmosphere of thunderstorms. It just happens over deeper layers, over colder layers where you can generate lightning. So although I'm going to be talking about thunderstorms and convection tonight, I'm going to use those terms interchangeably. It is important to realize that you can have basically convection without lightning. I've seen plenty of severe weather without lightning, so that's just something to keep in mind. Also, I've personally experienced thunderstorms with wind chills less than 0 degrees. I went to school at the University of Oklahoma. We get crazy weather there. You get crazy weather everywhere, but there's one time we had a storm in the middle of an ice storm, so literally we're like picking up pieces of hail amongst pieces of sleet and differentiating between the two. It was wild. I've also seen thunderstorms that are only about 10,000 feet tall. If they're right in that layer around minus 20 Celsius, they're going to generate lightning. So not all thunderstorms are the same. But obviously, a lot more fun comes from those really hot July, August days with oodles of CAPE, 8,000 joules per kilogram of CAPE. That's when you get your really big, prolific lightning-producing thunderstorms like we actually saw this past summer. All right, so let's talk about the difference between surface-based and elevated thunderstorms, because it's important to know the difference when we're expecting different hazards from thunderstorms. So surface-based thunderstorms, just like surface-based instability, they're most common during the daytime hours and in the warm sector of large cyclones. That's because the sun is out, it heats the atmosphere, it heats the boundary layer, you can get surface-based instability. Now, surface-based thunderstorms can also produce any type of severe weather, so that's damaging hail, damaging winds, flash flooding, and tornadoes. When it comes to damaging winds produced by surface-based thunderstorms, we generally understand the processes pretty well. So when it comes to downbursts and microbursts, cold pools and river flow jets, that's with squall lines like in the middle image right there, and small-scale circulations like tornadoes or mesovortices or MCVs like on the north side of a bow echo. The way that all of that happens, all of those develop, is pretty well understood. Some of you may be hearing or learning about that in your classes. And it garners a lot of attention because it happens pretty often in an average summer day somewhere in the United States. Now, if we contrast that with elevated thunderstorms, those are most common on the cold side of frontal boundaries, so north of the warm front, behind the cold front, often during the nighttime hours, because at nighttime the sun is set, the boundary layer cools, and you have a stable layer near the ground. They can occur any time of day, but usually, or at least most often, it's at nighttime. Now, operational wisdom, that is wisdom among forecasters, is that elevated storms only produce damaging hail and flash flooding. The thinking is if you have cold air at the ground like a stable layer, it acts like a cushion, like a big pillow. So if you have a big downdraft that's pushing into that cushion, it's not going to make it to the ground. So stable layers are thought to be that protective layer. This is a term that Ted Fujita coined in the 1980s, call it the cushion stage, where you can't have damaging winds. The reason why you cannot have tornadoes is because they require near-ground instability. So if you have a stable layer, the thinking is you can't have a tornado. There we go. Now, when you're looking at radar, you actually cannot tell the difference between a surface-based and an elevated storm. When looking at reflectivity, you really have to take into account the environment. So you have to keep track of where are our boundaries, where are warm fronts, where are cold fronts, outflow boundaries. When you have storms that are near boundaries, you have to be really careful to see if the storm is becoming surface-based, becoming elevated. Is it going to ride the boundary? Storms do really funny things along boundaries. It drives us nuts. They produce tornadoes like it's nothing. But if you just look at radar, you can't tell the difference. Someone who's really experienced can probably see clues when looking at velocity data, but reflectivity data, you literally cannot tell the difference. So you really have to be looking at the environments. All right, so what are mesoscale gravity waves? I have a video here. We're going to see if this works. It didn't work when we were testing, but just in case, I'm going to try to play it. Let's see if this loads. Oh, perfect. Yeah, that worked. All right, so mesoscale gravity waves, that's kind of a mouthful, but they are oscillations that are caused by pushing up and down on some stable oscillatory fluid. So that's my academic speak right there. What is it? So the atmosphere acts like a fluid. It's like a giant bathtub, a really, really giant bathtub. And what happens is anytime you have a stable layer, if you push down on it, you push forward, just like when you throw a rock into a pond, it's going to create ripples. Please don't do that. Let's not do that. That always happens at the worst time. All right, this is not my computer, it's someone else's computer. All right. So anyway, just like a bathtub, if you were to push down, you're gonna get ripples that move away. The same thing happens in the atmosphere, and this is a really dramatic example taken, I assume, from central Iowa based on whose video it is. You're not always gonna see something this dramatic. You don't often have the clouds that are fully condensed, but this is really sped up, and you can just see these ripples, these huge ripples propagating across the field. And it's actually probably crossing all of Iowa. And this happens in the atmosphere. Now, I do have another video here that's probably not going to work, but let me just get off of here and advance the slide. Yeah, it's okay. It's just another video of gravity waves. But how do stable layers develop, right? The first stage of even getting gravity waves is you need to have a layer where they can propagate through. Now, stable layers often develop at night due to nighttime cooling. It's happening right now outside. The temperature is going down. They also develop in the wake of showers and storms by precipitation. It's natural air conditioning from nature, from rising or sinking motion in the atmosphere. That's a way to cool or warm temperature in the atmosphere. Just purely the movement of air masses. If you have a cold front, typically you have a stable layer behind that cold front. And they can exist at any level in the atmosphere. So who here has been on a plane in clear air and had really bad turbulence? See some hands going up. That's typically caused by gravity waves. Clear air turbulence is almost always gravity waves near jet streams. Some of you have probably heard of the Santa Ana winds or downslope windstorms. That's a consequence of gravity waves. Gravity waves are everywhere. They're absolutely everywhere. They're ubiquitous in the atmosphere. We just often can't see them like we saw in that dramatic video. The thing is, they just haven't gotten a lot of attention. I think the attention that they deserve. This was a video, but it's okay. We can see the still image. There are multiple ways to generate and maintain gravity waves. A very common way to generate gravity waves in the atmosphere is from cold fronts and cold pools that are propagating across the plains or the Midwest. It's a little blurry here, but this is an image of a bore. It's an undular bore. So there's basically a cold front that's ripping down south through Texas. I think this was October of 2020. And right behind the cold front, you get these undulations. And this is very common this time of year. Anytime you get big cold fronts, if you zoom out, look at satellite, you're going to see these bores and these gravity waves everywhere. So cold fronts and cold pools are a very common way to generate gravity waves. Another way is just strengthening storm systems. A rapidly strengthening baroclinic low pressure system will actually generate gravity waves. They're typically a little bit higher up in the atmosphere, but it's another way to get the job done. Just the updrafts of thunderstorms or convective updrafts can generate gravity waves. By that way, when the air is warmer than its surrounding environment, it tends to expand and it pops and it sends waves going outward. And also topography. Mountains create gravity waves, especially when you have flow over mountains. So downslope windstorms develop from basically how the flow is changing over a mountain. It gets some pretty interesting fluid dynamics, but there's really a lot of ways to generate gravity waves, and sometimes all these effects work in tandem. Do have a schematic here. I can't help myself throwing a figure or two that shows different ways to generate gravity waves. The way to interpret this is the left three panels are one scenario, the right panel is another scenario. But on the left-hand side here, I'm going to deviate from this box. I can't help myself. But if you have basically a gravity current or a cold front that's pushing into a stable layer, it's going to lift that layer up. And the definition of stability is when you lift that layer, it wants to go back down. If you push it up or push it down, it wants to revert to its original position. So that layer is going to start to oscillate. And it can do some pretty funny things based on the temperature or the stability in the profile, where it could actually speed ahead of the cold fronts. It can grow deeper. It can get smaller. Can do all sorts of really funny things. And I mentioned another way to generate gravity waves is with rapidly strengthening low pressure systems. So on the right-hand side at the top, that's more of like a top-down view. Call it a 300 millibar chart. You have a rapidly deepening low pressure system, an upper level trough that's becoming negatively tilted. Oftentimes when that happens, you get a tropospheric fold and you get a pop and you generate gravity waves, typically downstream of the low pressure system. In the United States, most of our deepening low pressure systems move northeast. That doesn't always happen, but generally speaking. So that means that most of the gravity waves are going to move toward the northeast away from the center of the low. And then the bottom right is sort of like a cross-section of how that works. You can see the dynamic tropopause, the fold that's sort of popping and leading to the genesis of gravity waves. By the way, when you see some of the radar presentations in here, you're going to see these all the time. Once you see them, you can't unsee them. So I encourage all of you, when you see like a rapidly deepening low pressure system, look for signs of gravity waves in the radar field. And I'm going to show you what that looks like. Now, it may not surprise you that gravity waves and elevated thunderstorms are interlinked. They both require some sort of stable layer to occur. So they're inevitably interlinked. Now, any thunderstorm can produce a gravity wave, and gravity waves can produce thunderstorms. Sometimes it's a little bit of a chicken and egg problem. You don't know what comes first. But the thing is, they can really help out each other and make each stronger. So thunderstorms with updrafts can make a gravity wave stronger, and gravity waves can help thunderstorms become stronger by providing areas of updrafts and downdrafts or convergence and divergence. There's actually a whole instability theory that's based off of how thunderstorms and gravity waves interact. It's called ducted wave CISC. It's a mouthful. It's heavy math. But there is some really interesting research looking at that. And go forward here. There are very few operational methods. In fact, I'll go as far as to say there are no operational methods to forecast the interaction of gravity waves and thunderstorms. So we know that it happens. We just don't know exactly why and under what conditions. And as I'll show you, that's really problematic. I should say that there are methods to forecast gravity waves by themselves. In fact, the former director of the National Weather Service, Louis Uccellini, he started his career with some pretty foundational papers on gravity waves, looking at really impactful snowstorms in the Northeast. He was a big snowstorm lover. But in terms of forecasting thunderstorms and gravity waves, really not well understood. So what does this all have to do with damaging winds? I've been rambling off here about instability in thunderstorms and elevated layers and whatnot, but why are we here? We're here to talk about damaging winds. So I want to tell a quick story here. Before I came to the National Weather Service in Chicago, I worked at the National Weather Service office in Grand Rapids. That was right before the pandemic. And at the time, I was what we call a general forecaster. So a little look behind the scenes of how it works in the National Weather Service office. You typically have a lead forecaster on shift and then 2 to 3 general forecasters. And the role of the lead forecaster is to help set the table and set the expectation of who's doing what and being able to sort of move the pieces to make sure that the mission is completed successfully. On this particular day, I was a general forecaster. I walked in, and the lead forecaster at the time, Bill Marino, said, "Brett, we have storms crossing the lake. They're going to come on shore here, and we want you to be on radar to keep an eye on these." Now, we were not expecting severe weather this morning. This is a loop from about Eastern time. It's 9:02 to 9:18 in the morning, June 1st, 2019. We were expecting severe weather later in the afternoon, but not at this particular time. So when you step in to work radar, especially if there's storms already on the scopes, you sort of have to triage. You have to figure out which ones do I need to focus on first. So the first step of that is you have to have a basic environmental analysis. There was a warm front draped across the state this particular day. It went right through Grand Rapids. And I recognized there were 3 general areas of storms that I need to watch. The first was this little cluster coming offshore into Allegan County, just south of Holland. This is already on land, so I felt I need to look at that first since it was potentially already impacting people. The second area I wanted to look at was this kind of linear feature, kind of riding the warm front. The orientation of it didn't really concern me, but as I mentioned earlier, when you have storms along warm fronts or boundaries, they tend to do crazy things. And the third area I just wanted to keep a lazy eye on was this really showery activity. There's very little lightning north of the warm front coming ashore near Ludington and Pentwater. It looked pretty anemic to me. I really wasn't too concerned about it. Can anyone guess where the severe weather was? Based off of the discussion of the name of this talk, can you guess where it was? It was up north. Not expected at all. The storm further to the south near Holland produced pea to penny-sized hail. Great. The one in the middle did absolutely nothing. The storm up north was a monster. It produced widespread tree damage across Mason County. In fact, the entire county lost power. Most roads were closed because of downed trees. There was a meteo tsunami. That's literally a push of water came into Ludington. It flooded the harbor. It flooded homes and businesses downtown Ludington. And it had this crazy roll cloud when it came in. I mean, that roll cloud does not match the radar image. Wow. It's crazy. And when we're first getting reports of tree damage, I will openly admit I thought they were fake. I discounted them. I said, these people don't know what they're talking about. I was the one who didn't know what I was talking about. I was completely wrong. And if anyone who knows me, or maybe you've learned by me talking really fast here, events like this don't sit well with me. I don't like it when something happens that I don't understand. I don't like it when something like this happens with no warning. There were no warnings at all when this happened. And that led me to say, okay, we got to figure out what exactly happened here. So before this next slide, I'm going to skip ahead here. So in 2019, I worked in Grand Rapids, and I came to Chicago right before the pandemic. And in roughly about a year's time, I started saying, okay, we got to start looking at these events a little bit more. I reached out to some of my colleagues in different offices. I said, hey, be on the lookout for these strange events. If you talk to any National Weather Service meteorologist, they always have a laundry list of weird convective events they worked where severe weather happened. They didn't expect it. But after a while, we started to piece together that these events kind of have some similarities. They have a similar look and feel to them. unexpectedly producing damaging winds. And at the time, we thought they were confined to the Great Lakes. So we thought, all right, let's put together a research project here. So teamed up with a forecaster at the National Weather Service office in Rapid City, Keith Sherburne. If you're really into like severe weather, he's done a lot of work in like high shear, low cape parameters. So like the SHERB parameter comes from him. Also met with a professor at Colorado State University, Dr. Russ Schumacher. He's also their state climatologist. And we said, okay, let's put together a research project here. If you want to know the exact methodology, come find me afterwards. It's a little boring. I don't want to get too much into that. But we put together a pretty formal research project, a rigorous method to identify these events. And the first thing we wanted to do is get a sense of how often does this happen. So we built a very short climatology, 2021 to 2022, just 2 years. In like the academic world, 2 years is like nothing. I'm honestly surprised we were not dinged on that. But we just wanted to get a sense, is this something that's really rare, or does this happen all the time? And we found in just 2 years, we found 52 cases where you had like equally spaced bands of elevated thunderstorms, and about half of those were producing damaging winds. And we thought, well, that's strange. And we zoomed down and we found that this is happening everywhere. And I'm going to show a map of where this has happened. What we did with the study is we analyzed the radar data and the storm reports to determine if these events produce damaging winds. And then we documented a unique radar signature and an observational signature, so what basically people experience at the ground when this happens. And I'm going to show all of you that in the next few slides here. But first, I want to go a little bit over the climatology, focusing on the top left panel A for now. We found that these events are most common during the transition season. So roughly March through June is sort of a peak, and then another secondary peak, September and October. There's a dip during the summer months, during July and August, as well as a dip during the peak of winter, so that's like December and January. We think the reason why that this is most common in the transition season is that's when you have the overlap of instability, you're warming the atmosphere, you get engulfed moisture, and big low pressure systems, which I mentioned earlier, helps generate these gravity waves. In the middle of summer, you typically don't have big low pressure systems. Most lows are developed from actually like convective systems, not dissimilar from what's happening along the Gulf Coast right now. And then in the winter time, most instability is confined to the Gulf Coast, and along the Gulf Coast, it's really hard to get elevated instability because you have this giant like reservoir of 70-degree dew points, and if you have that, you're always going to be surface-based. So this is most common during the transition season. The top right, we found that this could happen any time of day, but most common during the nighttime, perhaps not surprising. But what was most interesting to me is the bottom left is the duration of these events. Most of them occur, in fact, greater than 80% of them last longer than 6 hours. Some of them lasting as long as 24 hours as they travel across the country. So this is not just like a single supercell or a single line of storms producing damaging winds. These are convective events spanning multiple states, lasting for like multiple shifts in the scale of the National Weather Service. And that was pretty interesting to me. We found this could happen anywhere. So just our 2-year period, we documented these events as far northwest as Washington State, as far southeast as Florida, as far northeast as Maine, really from coast to coast. I strongly suspect if this climatology were expanded, we would find it at pretty much any radar site across the country. I've seen it as far south as the Baja California coast of Mexico, just south of California. I've seen it in Canada. Happens pretty much anywhere you can get elevated instability or thunderstorms. So what does this look like? And this is, once you learn what this looks like, you're going to see them everywhere, I swear. So the first thing is, let's look at the radar signatures. So we call this gravity wave associated convection, or GWAC for short. I'm not sure why we picked that. I can't stand guacamole. I can't taste it, but that's what we're calling it. But gravity wave associated convection, it often manifests as 2 or more equally spaced bands that propagate in the same direction for more than 3 hours. And it can adopt numerous shapes and sizes. So the first example I showed in Michigan when I was working that severe weather event, it was just one little band, but if you zoom out and look over a longer period of time, there were multiple bands that crossed the state. I was just hyper-focused on Michigan. But these typically multiple bands. Now the spacing can vary. Let's see if get this to work here. There we go. The spacing can vary and the reflectivity can vary as well. We've seen cases where the reflectivity is really weak, only about 35 dBz, that's like yellow on the radar, to very strong or intense with like 65 plus dBz associated actually with damaging hail. Now the spacing can also vary between each event. They can be really tight, like within a county. They can be very wide across half of a state. And there we go. The storm mode could also vary from single cells to linear, like Boeing bands to supercells. I've seen it all. The defining characteristic is just the equally spaced bands. It doesn't matter what type of storm it is. And when you see what looks like outflow boundaries, again, I'm going to deviate from my box here. So these little outflow boundaries, that's actually the leading edge of each gravity wave. Those are not outflow boundaries. So that's another thing that's really easy to misidentify. So not to get ahead of myself here, a lot of National Weather Service meteorologists think, oh, the winds are occurring behind, with the actual storm, not with the outflow boundary. Actually, the damaging winds are occurring with that boundary, not with the storm itself sometimes. But I'll show that a little bit later. And the character of the reflectivity does not always offer predictive skill and damaging wind potential. So I'm going to show a 16 panel here. I know it's a little small for anyone in the back, but it takes on all different shapes and sizes, different storm modes, but it's not always easy to say, okay, out of these 16, which 8 are severe? So half of them are severe, half of them did not produce any damaging winds. And sure, maybe some of the cases where you have really high reflectivity, looks like you have giant hail cores, those are the severe ones. Yeah, that helps a little bit. But how do you explain the ones that look like crap? The ones at the top middle there look really weak and anemic. Those produce sig severe winds, 80 mile-an-hour wind gusts. This one right here, this is going to be the lower left, measured 80 plus mile-an-hour wind gust. It's really challenging as an operational meteorologist to look at radar and get like sig severe winds when the storm looks like garbage. And that's what's happening with these events. So the strength of the storm itself does not seem to be a factor in the strength of the winds. And I also want to provide an opportunity to see what this looks like on a large scale, not to be hyper-focused on a specific area. So there's a lot going on in this radar image. This is from 2018 in April, so right in the peak of when these events typically occur. I should have added an L to the map. There's a rapidly deepening low pressure system going from basically like central Kansas to like northeastern Nebraska at this, within this loop. And there's multiple scales of gravity waves. You can start to see multiple bands of waves propagating across the Great Lakes. So the first couple bands move across Wisconsin to Lake Michigan and into lower Michigan. Those actually produced another meteotsunami in Ludington. I don't know what's up with Ludington. They're like the Moore, Oklahoma of like elevated convection for some reason. They've had multiple events like this. But that meteotsunami was like 8 feet high. A little behind the scenes, there's like I believe it's an electrical facility up near Ludington, and I believe that their storage facility potentially had some problems with this amount of water coming in, so it can be very impactful. One of the convective bands that went across southern Minnesota, I'll point it out here when it resets. It was that band right there. That produced measured wind gusts in excess of 80 miles an hour, blew some semis off the interstate. It did that while it was snowing, so not always producing rainfall, completely wild. And you see a couple other bands, gravity wave associated convection going across North Dakota. Did not produce damaging winds, but produced damaging hail, not in an SPC outlook. So these storms give us grief. Completely unexpected, completely unwarned, producing high impact severe weather. And this is pretty typical when you have a rapidly deepening storm system. So again, I encourage all of you to look at radar imagery this fall or next spring and look for this, and you're gonna see it. I'm hoping everyone starts to see this more and more. So that's what it looks like in reflectivity. What does this look like in velocity? So we're going to look at one case in particular here. This is going to be a case for May 15th, 2022 at 5:30 in the morning. Not a typically favored time for severe weather, generally speaking. So we have 3 convective bands going from Nebraska into Kansas. So if we zoom in, the left-hand side is going to be reflectivity, the right-hand side is going to be velocity. I realize most people in the room are familiar with velocity, but I'll still do a quick refresher on how to interpret it here. Anytime we are interpreting velocity data, you always have to know where the radar is located, so you can have a reference point. And green is always going to be moving toward the radar, red is moving away from the radar. So in this particular case, we have a southeasterly wind, that's wind coming from the southeast because it's green toward the radar, red away toward the radar. So in this particular case, I think the damaging winds stand out pretty clearly, but I'm going to add another annotation here. That's the leading edge of radar reflectivity, so on the left-hand side. And notice where all the wind is. It is out ahead of the reflectivity. So that is strong northwesterly winds blowing greater than 70 miles an hour. And these damaging winds are occurring ahead of the reflectivity and basically up to where it looks like there's that outflow boundary, but again, that's the leading edge of the gravity wave. And this presents quite a challenge for operational meteorologists. A lot of times we're taught that in regions of weak reflectivity, the velocity values can't be trusted. And yeah, sure, that's true sometimes, but the fact of the matter is when you see this feature across multiple scans, you have to think, okay, something's going on here. And this velocity signature is repeatable across all of the events. If I actually go back here, notice that when the reflectivity, let's say, moves over a point, the winds die off. So all these damaging winds are occurring with no rainfall at all. once the rain starts, the winds are done, which is kind of challenging the message. How do you tell someone, hey, you have this storm that you see on radar coming, but all the damaging winds are going to happen before it rains? Really difficult. But here's just a few more cases across the country at different times. The velocity signature is repeatable. Now, of course, it's going to look a little bit different based off of where the radar is with respect to where the storm is. So just as sampling rotation in a storm is going to look different when you're like 80 miles out compared to like right next to the radar, the same thing happens here. But generally speaking, it looks pretty similar. The top left case is pretty interesting because this is actually a divergent couplet. So at the ground, you had winds kind of like opposing each other. But this is the signature we see among all of our cases, at least the ones that are producing damaging winds. And the skinny is the velocity values are real. They're representative. You know, anyone who's interrogating radar data, you still have to watch out for like artifacts like side lobe contamination. That happens when you have a really strong gradient reflectivity with supercells. But generally speaking, the message that at least I'm giving the National Weather Service forecasters is trust your velocity. If it looks funky to you, investigate it more. If you see it across multiple scans, it's probably real. And that's the message I'm giving all of them. And the other interesting thing is we can take cross-sections through the velocity signature to see what this looks like when you're looking through height. So this is a case that occurred in 2014 near La Crosse, Wisconsin. And cross-sections, I'm going to zoom it up on the next slide here, but it shows that there is no connection with the actual storm, like a ruin flow jet with the storm, and the damaging winds at the surface. So it's completely independent of, apparently independent of the storm. You may be able to actually visualize oscillations in the stable layer, and I'll point those out in just a moment here. But there's no signs of like microbursts, downdrafts, or ruin flow jets, cold pools, or circulations associated with these damaging winds. It's a completely separate process. So let me zoom in here. So this is the cross section. So from left to right, that's northwest to southeast. And you can see that layer in red, that is actually our stable layer. And it's separating between the damaging winds and the storm itself. There is a ruin flow jet that's not reaching the ground. So you can see right there, especially there, it's completely separate. And then once the loop gets toward the ends here, see how the green is oscillating back and forth? That's your gravity wave. So it's pretty cool that you can actually see this being sampled by the storm. So completely independent from like a ruin flow jet or other damaging wind mechanism. So that's what it looks like on radar. The next question is, what does this look like on the ground with observations? So we're going to compare and contrast observations from like traditional surface-based damaging winds. We're going to be looking at observations from Aurora, Illinois, during the August 10th, 2020 derecho. That's about as surface-based as you can get. And then on the right-hand side, we're going to be looking at the same exact case from La Crosse, looking at the observations and compare and contrast them. So in all these plots, left-hand side is going to be Aurora, right-hand side is going to be La Crosse. The orange, that's going to be the wind that's measured, and then the red's going to be temperature here. So in Aurora, with the derecho, when it came through in 2020, there was like a measured gust of 61 or 62 miles an hour. But notice the big drop in temperature. So we've all been outside, whether we want to admit it at all, in the middle of a storm. When a gust front comes through, you feel the cold air, right? That's the natural air conditioning. So when the gusty winds arrive, the temperature goes down. That's like the hallmark of an outflow boundary passage. When it comes to these gravity wave events, look at the red line. It's like completely like not moving at all. The temperature doesn't change. So when this happens, you're outside, you get like a 60-mile-an-hour wind gust, and the temperature is the same. Sometimes the temperature actually goes up by a few degrees. Some of you may have heard of heat bursts before. It's not the same process, but sometimes, as I get into the process in a minute here, when you have downward mixing of air, the temperature can rise a little bit. But this is not like literally a precipitation-driven downdraft causing these damaging winds. If we look at the wind direction on the left-hand side first in Aurora, you can see that the wind direction, let's see, do I have it on? Oh, I guess I don't have the scale on there. That's bad on me. But it basically became a westerly wind direction there. And the wind direction stayed westerly after the storm went through. It's pretty common with surface-based systems. You get a big gust of wind with the wind shift, and the wind shift takes a long time to revert back to the prior wind before the storm arrived. With these elevated events, these gravity wave events, you still get a wind shift, but once the damaging wind cease, the winds return to what they were beforehand. Very bizarre, not something we typically see with surface-based systems. And then finally, looking at pressure in the yellow line, with a traditional surface-based system with the derecho, you have a big pressure rise, a big pressure hump, and it takes a long time for the pressure to return back to normal. It's just taking time for the cold pool to move through. Whereas on the right-hand side with the elevated system, you actually have oscillations in pressure. That's associated with each wave crest going over the station. And not only that, look at how, at least with the first wave, the pressure hump, the winds, the magnitude is actually correlated pretty nicely. And that is the hallmark of the passage of a gravity wave, where the pressure and the wind are correlated like that. So that's also pretty unique. This is not the same process that causes damaging winds in surface-based systems. So we're going to spend a little bit of time on this slide. So what the heck is actually going on? I was very lucky to link up with Dr. Russ Schumacher out of Colorado State University because his research team actually discovered this process. They thought it was a one-off. They thought it was a one storm that happened to produce damaging winds this way. They wrote up this paper because they thought it was really cool. And then Keith and I came to him and say, oh, this happens all the time. And it blew his mind. So we mutually blew each other's minds when we realized this is happening. So what's going on here is it's called gravity wave braking. So on the left-hand side, this is a loop. So it goes from height on the y-axis. The x-axis is actually going from south to north. So this is a cross-section from south to north through a storm that produced damaging winds. And this is a model simulation. The black lines, those are contours of potential temperature. You can think of it like temperature. You can see the blue shading illustrates the stable layer very nicely. You can see the red shading illustrating, you can think of it as basically elevated instability. You can see with time, basically development of a gravity wave. You can see basically the upward hump in the temperature that's associated with the gravity wave. And with time, as the simulation goes on, notice how it gets pretty squirrely. So ignoring what's going on in the red, look what's happening in the blue behind the gravity wave. It gets really jumpy. Basically, your isotropes or your lines of temperature are becoming overturned, and they're becoming really squirrely, and that's indicative of a gravity wave braking event. So I think most of us have at least seen pictures of the beach, but a lot of us have probably been on the beach. You've seen waves coming toward you. You see when the wave is really far out, it's kind of laminar and smooth, but when it gets close to the shore, it breaks, right? You get that crest. Now, that's happening because of the slope of the beach. It's not the same process here. But what's going on here is the gravity wave is propagating. It's getting big. It's getting really deep. And there's a certain level at which it can't grow anymore, so it breaks. It just overturns on itself. And that's what's going on in these events. And then when you're under this breaking gravity wave, you can think of like a hydraulic jump. It's really turbulent. It's really nasty, and you get damaging winds. And that's what's happening with these. It's a very similar process to downslope windstorms, the Santa Ana winds I mentioned earlier. It's not exactly the same, but it's similar. And in the academic world, it's called up-down paths or up-down trajectories. So the air that's participating in these damaging winds, completely independent of the storm, it's actually originating from ahead of the storm. The stable layer is not preventing the damaging winds. The stable layer is participating in the damaging winds. It's getting lifted up, and then it's crashing back down to the surface. So completely foreign and not necessarily expected. So these events pose an immense forecasting challenge. Methods to forecast gravity waves are not regularly practiced by operational meteorologists. So forget about the thunderstorms. Just gravity waves themselves are not forecasted. And even in like recent weeks, I'm always reading academic journals and trying to read more about gravity waves. I'm actually a little frustrated with how much is out there that is simply not like taught to meteorologists. There's a lot of papers in the 80s and 90s and early 2000s looking at how to forecast gravity waves that just haven't become mainstream. But that's just forgetting thunderstorms. If you add thunderstorms to the mix, no one's forecasting that. I don't know how to forecast that. So there literally is no modern day method to forecast these. High resolution model guidance can do okay. Ever since I've been working on this project, I'm watching like the HUR, the NAM 3 kilometer, some of the WRFs like a hawk, where we have favorable synoptic pattern for these. They can do okay by forecasting like equally spaced bands of thunderstorms, but they have substantial false alarms, substantial missed events. They're often off in location as well. Trying to be proactive by like sending emails to potentially impacted offices saying, hey, the HUR shows these gravity wave convective events moving over you. Keep an eye out. And then like the gravity waves happen like 3 states away producing damaging winds. It's just great. So high resolution model guidance is not perfect, but it can perhaps show some skill. But these events can be incredibly damaging. I didn't get into this too much, but some of the winds from these storms are well over 100 miles an hour, and that's not estimated, that's measured. I know of a couple cases where the winds were like 112 miles an hour, produced widespread wind damage, injuries, structure damage. There's even reports of tornadoes, which makes 0 sense. Never say never. I used to think that elevated convection can't produce damaging winds, and I've found that's evidently not true. Pretty sure they're not producing tornadoes. I think it's something else going on, but what I take from that is it produces tornado-like damage, enough to confuse National Weather Service meteorologists to call them tornadoes. One particular case is pretty local. I say that as someone who goes on surveys, so yeah, you can quote me on that. Relative to this, nothing else. But anyway, one interesting event local to this area in 1996, which I realize is probably before most people were born in this room. I was only 2 years old, but that was a high-risk day for any weather history buffs. Big tornado outbreak across central Illinois, central Indiana. So, yep, I see some of the old-timers remember it. It was a big event. It was a really big event. Hey, I knew about this event, too, because I'm a big weather history buff. So, but what's really interesting is there was supposedly an F2 tornado in Zion, Illinois, which is in northeastern Lake County. And the way the story goes with this event is our senior service hydrologist, his name is Scott Lincoln, he is an extraordinaire. And he was just remapping tornado paths, and he looked at this one and he said, Brett, this is really bizarre. Why was there an F2 tornado right next to the lake when it was well north of the warm front? And I said, well, I bet I know what that was. It was one of these gravity wave events. And we actually looked at all the storm reports from this particular storm and found that there was a huge swath of damaging winds that started in Stevenson County, went all the way to the lakeshore, with widespread 60 to 70 mile-an-hour winds and pockets of 100 mile-an-hour winds. So this F2 tornado was probably just one pocket of 100-plus mile-an-hour winds in a long-lived windstorm. And I'm not putting down the forecasters at the time who called it a tornado. We just didn't know. We just didn't know. And I take that to mean that these storms can produce tornado-like damage. So one struggle that we still have is that the operational wisdom that elevated storms can't produce damaging winds remains. Every time I read an area forecast discussion that says something along the lines of the stable layer will prevent damaging winds, I'm like, oh, I need to email them because that's just not true. The stable layer is participating in the damaging winds. So where do we go from here? What's next with GWOC? So right now we're in the middle of a preliminary analysis of GWOC environments, trying to see if we can differentiate the types of environments that produce SIG severe damaging winds, just regular severe damaging winds, and non-severe damaging winds. Probably still a little too early before we have preliminary results, but we're looking at it. What we're more excited about is we're collaborating on an NSF grant with 2 universities to kind of take this and run. As much as I think these events are really cool, I simply don't have the time to do model simulations or expand the climatology. I don't have the resources, and it's also just not really my job. My job is to forecast the weather, not to investigate these kind of events. So we're hoping that we can write up this grant proposal and get funded and have grad students basically take it and run. And I'll be really excited if that's what happens. But most of all, we're just trying to get the word out. We're developing forecaster training, trying to present it as many forecaster workshops as I can. And also presenting here to groups like you to get the word out that elevated convection, elevated storms produces damaging winds. So thank you for your time, and I believe we should have some time for questions. Yeah, there you go.
There we go. My jaw is firmly planted in the ground over there. This is amazing stuff. Before we start taking some questions, if everyone's invited, we're going to Warren's Ale House over in Donata Square. If anyone wants to continue this discussion, because I got some thoughts for you about some of this.
Awesome.
It's like, yeah, this is awesome, but this is crazy. So, questions we have in the back over there, Mike, back row.
Get my clicker.
Good evening. Thank you for that talk. That was fascinating.
Yeah.
Couple of questions, really just one multi-part question. For the sake of forecasting, how much of these signs that you're looking for are environmental in nature? In other words, is this something that might be parameterized? I'm thinking of supercell composite. Could you make an index to help even just look at model output to help identify where that might pop up?
Yeah, I think the dream is to make a gravity wave breaking parameter. Unfortunately, what we're finding is the environments that support these are really tricky to identify. Not to get too into the weeds, but gravity wave dynamics, it's if you think of difficult math, it's one level above that. It's way above my head. So being able to trust the model to even get that correct is really difficult. But the hope is that you understand the environment first. Maybe you create some sort of parameter. Once you can forecast that, the rest comes from it. Sort of like if you have an STP of 10, I don't care what the storm looks like, it's probably going to produce a tornado, right? So environment is first. So hopefully we get to there at some point soon. Thank you.
I got a question right
Yeah.
here. Is it on? Yeah. My question is, you were talking about when you were looking at the high resolution models, and then you were basically making a statement about these situations when they are synoptically evident. That's when you're taking a look at those high resolution models. So my question is, what are some synoptically evident conditions that occur that can allow for these gravity wave situations?
Sure, yeah. Let me go way back here. Maybe it's faster just to jump out. There's a plot here that shows like a 300 millibar map. So just a rapidly deepening low pressure system is really what you want to look for. I don't know. Let's see slideshow present. Here we go. So the right-hand side, sort of the cheat code is if you have a jet streak that's curving around the base of a trough. So if a trough is becoming positively tilted, negatively tilted, so I guess it's like that for your perspective. A jet streak that's going around the base of that trough with a deepening low pressure system, almost always you get gravity waves. So rapidly deepening low pressure system, that's really what you want to look for. Now that is not always the case. We have some events where it seems like the gravity waves develop with the thunderstorms independent of a low pressure system. I can't forecast those right now, so hopefully we can get there sometime. Thank you. Yeah.
Other questions?
I think you helped explain something to me. I'm going to really show my age because this happened before I became a student of Tom Skilling, and now he's retired. Anyway, I was an avid golfer, and I went to Winnetka Country Club, okay, one day, and there was a forecast of some rainy weather coming. And I'm on the 18th hole, fortunately, and off in the west it's getting very dark. So I kind of scampered across the parking lot and put my bag away and got in the car. And it poured rain. I decided I'm going to just stick around until it clears out. And then I decided, well, when it clears out, I think I'll go to what we call the 19th hole, which is where you get drinks.
Restaurant, yep.
Yeah, that's right, yeah. And the sky gets black to the west again, okay. Big storm comes over. Another big squall line, it looks like. And then wait for that to clear, get back out to the car. Sky in the west is getting black again.
Mm-hmm.
What in the world's going on here? So I wait for that to clear. And I start going home. And the sky in the west is getting black again, another squall line. That's 4 in one afternoon. I'd always been taught that, you know, when you get one to go through, it just stabilizes everything. Mm-hmm. Maybe it was one of these.
Do you remember the date?
It would have been early summer, probably of 1968 or so.
Oh, okay, yeah, that's further back than I've looked.
Yeah.
In the 60s, yeah.
Yeah.
It could have been. I mean,
I was just becoming 21 years old. I was just able to drink, you know.
I got you, yeah. Yeah, it could have been one of these events. Also, just regardless of gravity waves, elevated convection also can just parade over the same area since it's not necessarily feeding on surface-based instability. If you have like a low-level jet that's like feeding a new instability into elevated convection, it can just keep going. A lot of our biggest flash floods are actually from elevated convection. But if you had these big like jumps between the storms, I guess gaps between the storms, could have been one of these events. It's funny, we've talked to like some storm prediction center meteorologists or forecasters there before, and like Rich Thompson, Roger Edwards is the big name, Rich Thompson is another one, which by the way, I want to hear more about that Roger Edwards thing. But Rich Thompson was like, oh wait, I've seen this before. I mean, they look at this every single day, and even to them, like the light bulb went off.
Yeah,
and I need to talk with them more.
I talked to a meteorologist immediately afterward, maybe about 3 weeks later. He said, that's impossible. You can't have that. It doesn't work that way.
That was me like 2 years ago with damaging winds produced by elevated convection. Yeah, so, the atmosphere is amazing.
So I have a question kind of concerning this. The conceptual model I have is if it's a stable layer, you can keep the gravity waves contained. Mm-hmm. In an unstable atmosphere, won't you get a runaway? You'll get one-sided stuff. So how would you get instability in the afternoon with something like this where there might be some serious instability coming in between some other gravity wave? Is it a surface base or is it ducted in stable layer somewhere higher up?
Yeah, so I think there's a couple things in there. The first thing is the stable layer a lot of times acts as the lower bound for the layer where gravity waves are propagating. So when we're forecasting or looking at gravity waves, the layer where the gravity waves develop, it's bounded by your temperature inversion, so that's the top of your stable layer, and then something called a critical layer. It's not intuitive at all, but a critical layer is defined where basically the wave relative wind speed is 0. So it's where the ambient wind speed in the atmosphere matches that of the wave. And due to some crazy wave dynamics, when that happens, a wave can no longer grow. It becomes trapped. And under certain conditions, which I don't fully understand, I'll admit, the gravity wave breaks. So that's one part of it. And that critical layer can actually be an unstable layer, like a convectively unstable layer. So one thing we're looking at is what's the instability sort of in this wave growing layer? Is that a discriminating factor? But in terms of replenishing instability, a lot of times when you have elevated convection, whether it's just due to geometry or just the way the dominoes are falling, you often have a low-level jet, which is replenishing instability. So that's why, like, even if an elevated storm uses a little bit of instability, there's just more building in behind it. So it's like a cheat code.
So when you did that one really cool, like the breaking of the wave, that's behind the leading edge of the wave?
Yeah. Oops, I mean,
And then did you do stuff with like Froude numbers? Because first thing I saw, and then I'm like, oh, that's a hydraulic jump. And
Yeah.
then you started saying, I'm like, yeah, that's really amazing.
yeah, it's not exactly the same. We don't think it's the same, at least. The spectrum of wave dynamics, I mean, you have like high frequency gravity waves, you have mountain waves, which deal with like the Froude number that basically is like how the flow is changing from, I think it's like supercritical to subcritical, right? Yeah, that's something that, at least in like Russ Schumacher's paper, they're the ones who really investigated the process. They said it's not exactly synonymous, it's not exactly the same. And one thing they struggled with is, where do we place this in the framework of gravity waves? And I think a lot more work needs to be done to fully understand what's going on. And truth be told, there's probably multiple ways to get the job done, just as there's probably multiple ways to produce a tornado, multiple ways to produce damaging winds and a surface-based storm. So I think that it's possible that the events that we've modeled so far are just like a finite number or finite like way that this can happen with gravity waves.
Okay, cool.
This could also happen independent of convection. So like sometimes if you have like a huge burst of damaging winds on the backside of like stratiform precipitation, it's a gravity wave. So there's other ways that gravity waves can produce damage independent of thunderstorms.
When something like this is happening in the Chicago CWA, what are you looking for, and how quick is your office now to jump on something like this?
For better or worse, the staff at our office gets a ton of emails from me when stuff like this is coming up. So they're usually like, it's on their radar, so to speak, when these events can happen. This is something that we're all going to be ready for in our office, at least. We're trying to spread it across the weather service to at least be familiar with this. What I'm also teaching everybody is keep an eye on observations. So sometimes, like in the middle of the night, if you get a random wind gust of 60 miles an hour out of a storm you think is elevated, it's very easy to say, oh, that ASOS station isn't working. It's a bad station. So what I'm trying to reinforce is, no, actually trust your data. If you have the radar signature, you have a measured wind speed, you better have a warning out. Get that out. So it's basically trusting the data you have. Yeah.
How did you do that day with your warnings in Michigan?
Oh, horrible. No warnings at all. Zero. Yeah, and then we had supercells that afternoon produce baseball-sized hail. Those were warned, but no, not earlier in the day.
Any other questions? Hold on a second.
Oh, Helene, or not Helene, or what is it?
Milton.
Milton, yeah, I can't keep
Milton.
them.
You can't be afraid of Milton.
Yeah.
We're going to just take a look at quickly at what the hurricane's doing. This was great. I mean, this is just amazing. I hope that we can get some responses, and we're going to promote this video and try to get this out there. Cool. Those of you in grad school, take it back to your professors and talk about it and bring this up, and let's keep the word spread. So my students, thank you for being here. Just email me, and you'll get some extra credit. I don't know if any of Ron's students get extra credit. They do? Okay, beautiful. So anyway, here's our hurricane. Let's pull up the radar composite. I don't know, has anybody seen any reports? No, just pull in, there we go. So Tampa Bay is getting some serious part of the eye wall. And I think if you took a look at some of the models, like the highest wind gusts were definitely on the northwest quadrant of this thing. The open eye wall on the south seems to really take away some of that momentum brought down in the eye wall. So the Tampa Bay itself is getting some of the big stuff, and I don't know, that's probably where the worst surge is going to be. I don't.
Sarasota's already up to 10 feet.
10 feet at Sarasota, which is just down here over here.
Above all of our heads.
That's kind of where but that should be the max.
I think so, yeah.
So it'll be interesting to see this. A lot of flooding.
Those supercells also off the coast. I don't know if anyone was watching. Some of the craziest like tropical supercells I've seen in a long time.
The wedge in Fort Pierce, that was
Yeah, it's unreal. Very unusual.
Legit supercells with clear slots and
Yeah.
big wedge
Wild.
tornadoes. It's amazing. So. Huh?
Yeah.
Related to Milton, do you think that trough that was also like supposed to be kind of shearing apart, is that contributing to the tornadoes, at least in any sense, you think?
Could be.
From what I was seeing today, you had an unbelievable thermodynamic environment, and the winds were accelerating into that rapiding low pressure. So you had these really strong southeast winds. Andrew, you posted a photograph coming out of Tampa Bay. It was a big photograph. And with the instability, I don't know. Did anybody see what the Cape was today in that region?
Yeah, like
Couple 2,000.
Yeah,
So
that's
it was a
pretty
big severe weather outbreak. So it was legitimate storm. The SPC had EF2, hatch marks with an enhanced risk. So it was significant. It wasn't just your typical tropical cyclone tornadoes. It was pretty
I can't
serious.
think of the last time they had like a 10% hatch tropical. Yeah, I don't. Yeah, I don't think.
Excuse me, question back here.
I was just hearing like a lot of on the news that it could be a theory that Hurricane Milton might be able to reach a Category 6, maybe even a new. I just want to confirm whether that's true or not. I highly doubt that there's even going to be something like that. I mean, obviously, due to the chain, there's going to be some outbreaks of the storm,
Okay.
but I highly doubt it will even reach a new.
Yeah, I read about that. This one hit a maximum pressure of 897, and there has been plenty of hurricanes with lower pressures, plenty of hurricanes with larger, much larger diameters, stronger winds. I mean, this was a pretty good setup for I don't know, saw blade type of hurricane that it would be. The person who kind of quoted that is sort of a climate activist and wanted to kind of push that narrative. And the people who I really respect in hurricane forecasting kind of dismissed that pretty rapidly. It's, in my opinion, garbage.
Kind of like the EF scale, the 5 is open-ended at the top end. So even if it produced 600 mile per hour winds, it would still be considered a 5 in the current scale.
Yeah, and you'll see that somebody will say, well, let's call it an EF6, and it doesn't work that way.
Yeah, it's open.
Kind of doesn't work that way. So, I mean, it was a big storm. Ron, I think we were talking about it. It was pretty well forecast to shear out as the hurricane hit land, and I knew the winds were going to be much lower. It's still a big storm, but that storm surge is really probably the devastating part of it. It is becoming extratropical, Marissa, with that trough, so it'll quickly move to the east into the Atlantic and lose its tropical characteristics. Okay. All right, guys, thank you so much. I hope you have a great evening.
Thanks so much for
Yeah, no
doing that.
problem. Thanks for the invite.
Man,
It's
I tell
awesome.
you what.
That was unbelievable.
Oh, thank you.
I'm like,